Hello again, this is Professor Bennett from digitalaudiotheory.com. This programming example comes from Chapter 5, which covers quantization. Now, in the last programming examples, we saw that quantization introduces an error to the digital signal. In the best case scenario, an analog value will sometimes land exactly on a quantization level, and at these samples, the quantization error is 0. But at the worst case, the analog value lands exactly or nearly exactly in between two quantization error levels, meaning that the error will not be greater than positive q over 2 or less than negative q over 2. The quantization error is equally likely to land at any given point between two of these quantization levels, which will be demonstrated in this programming example. This is known as a rectangular probability distribution function, or RPDF for short. The RMS value, or the average level of an RPDF signal, is equal to its range over root 12. So for quantization error, its theoretical RMS level is Q, again because the level ranges from negative Q over 2 to positive Q over 2, giving us a range of Q. So Q over root 12. This is the RMS level of our quantization error. This theory will also be put to the test with the following programming example. So let's get started by generating a 100,000 point random sequence using the rand function. This is going to give us a rectangular PDF, random signal. Next, okay, so you can see what we're doing here actually. So we're creating 100,000 points in the range of, this is going to be in the range of 0 to 1. We're going to multiply that by 2 to put it in the range of 0 to 2. Then we're going to subtract 1 to put it in the range of -1 to +1. Next, we're going to take that signal and we're going to quantize it down to 8 bits. So here's our quantized random signal. Since we're in the range of +1 to -1 and we're using 8-bit encoding, then the quantization step size, which falls between plus or minus q over 2, in this case is going to be equal to plus or minus 1 over 256. And the PDF is going to be approximated down here with a 50-point histogram with box edges corresponding to the limits of the error signal, so at plus or minus q over 2. Here we put on, as the type of normalization that we're going to use, we put on PDF, which stands for probability density function. And this is going to affect the vertical axis scaling by setting the height of each box to the number of observations within that bin divided by the total number of observations times the width of the bin. This is meant to essentially have the histogram simulate a PDF. So when we plug in, okay, so first we generate the error by taking our original signal, subtracting out the quantized version. What is left is the error. We're going to save that as EQ. We're going to pass that EQ to the histogram. Let's take a look at what we've got. In this case, we need to set A equal to 1, the range. The amplitude. And we had set N equal to 8. Actually, you know what? Instead of grabbing Q like this, let's grab it just like this. Let's grab it out of here. Q. There we go. Here we have the probability, well, the histogram that is meant to approximate the probability density function. A PDF is truly continuous, so as soon as we discretize it, then it's no longer truly a PDF. But this is going to be pretty close. And you can see we get some wiggles up and down, but more or less these are hovering around this 128 mark. Okay, which if we look is exactly equal to 1 over q. If you recall the example with rolling the die, There's 6 possible outcomes, and so the probability of landing on any particular side is 1 out of the total number of outcomes, 6, 1 out of 6. Here the error can land anywhere from minus q over 2 to positive q over 2, so there's q possible values for the error to land at. So the probability of any such error is 1 out of the total possibilities, 1 over q, which is 128, which is exactly where these are falling. Now your mileage may vary. It should be apparent that the overall shape of this PDF is rectangular-ish. Adding more data points to the input sequence up here will result in the PDF becoming even more squared off. So if we make this 10 million points and redraw it, it becomes more square. So next, let's check the theoretical RMS of the quantization error and the actual RMS. So theoretically, we said it should be equal to q over root 12. This is the estimate, 0.0023, okay. Now let's check the actual. The actual, we take all of the error. There's no mean to this error, it's 0 mean. And so we can square it, take the average value, and take the square root. This is the RMS. This is the actual RMS. Let's see what we get. Matches, 0.0023. And on the next programming example, we're going to look at a way to reduce the perception of this quantization error, because yes, it can be heard. So I hope you enjoyed. Thank you.